So we talked about exponential functions, right, and what it means for an exponential expression, to have an exponential expression. So let's look at the flip side of that, logarithms, the inverse function of exponents. So a logarithmic function looks something like this. Okay, but that doesn't really mean anything to us, right? The question is, what does a logarithm actually mean? Well, the easiest way to think about logarithms is like this. If I said, for example, what power should you raise 3 to get 9, what would you tell me?
3.
Raise 3.
Oh, to the second power. Sorry.
Right, so it's second power, right? So we're going to say that we need to raise 3 to the second power to get 9. This way of thinking is exactly what a logarithm is. So, for example, if I say that log base a of x is equal to some number, that's the exact same thing as saying that I need to raise this value to this exponent to get this number. These are equivalent statements. So for example, what power should I raise 3 to get a 9? Well, the way I could write this in logarithmic form is I could say log base 3 of 9 is equal to what? Okay. Or if I want to be a little more algebraic about it, I could say log base 3 of 9 is equal to some unknown value, right? Some value of x. And this is equivalent to saying that 3 raised to the x power is equal to 9. And so what is that x value, right? And then we say that, oh, x has to be 2 because 3 squared is equal to 9. So that's all the logarithm is. When I say a logarithm base something of a number, it's just asking what power do you need to raise the base to in order to get to that other number. So you can see where this has a relationship with the exponential functions, right? We could write any expression as either a logarithm expression or as an exponential expression. You can go back and forth. So then I could maybe ask, we'll do another simple one. What is log base 2 of 8? In other words, what power should you raise 2 to in order to get 8? So if I wanted to write it like that, I could then put it into the exponential form and say this is the same thing as saying 2 to some power is equal to 8. So what is x here?
Third power.
Right, so x better be equal to 3, right? So we'll say that logarithm log base 2 of 8 is equal to 3, and that's exactly what we mean when we're asking for the logarithms. Trying to see exactly what exercise I'm going to assign from the other side. Okay, good. All right. So what about this log base 4 of 1/16? So what power should you raise 4 to get 1 over 16? 1 over 16. You can say if it's equal to x, it's equivalent to saying 4 to some power is equal to 1/16. In this case, it's actually easier if you can rewrite this as the exact same base, 4 to some power. If the two bases are equal to each other, then the two exponents will be equal to each other. This is a rule that we have if they're both, for everything except for 0, right? Because 0 raised to any power is 0, and 1 raised to any power is always 1. So as long as the base is not a 0 or 1, if we can get the two bases equal to each other, then we can just set the exponents equal to each other. And that's actually probably a rule that we should write over here that in b to the x is equal to b to the y, then that means that x is equal to y. As long as b is not equal to 0 and not equal to 1. And I guess we should also say, actually, the normal way this is written, because negative 1 also doesn't work, so I kind of wasn't thinking there. We'll just say that b is going to be positive, because we're not going to be dealing with negative bases either. So b will always be positive, and b will never be equal to 1. So should cover everything there. So do we figure out what this is how we can do this then? Well, maybe I can rewrite 16th as 4 to some power?
4 to
Maybe that one, right? Because really 1 over 16 is 1 over 4 squared. And so 4 to the x, 4 to the negative 2. Our rule says as long as b is not equal to 1 and it's a positive value, then this should work out fine. So I'm going to say here that x is equal to negative 2. So in fact, log base 4 of 16 is equal to negative 2. Okay. And probably if you thought about it long enough, you probably would just figure it out without necessarily having to do the equation over here. But you can always do the equation if it helps. What about log base 3 of 1/3? What would that be equal to? So if I want to use the equation, I'll say log base 3 of 1/3 is equal to some unknown. And then the exponent version of this would be what?
3x equals 3.
3 to the x power equals whatever's right here.
1/3.
Yeah, so 1/3. Okay. Well, if I want to write both of these with the same base, then 1/3 with a base of 3 is
3 negative 1.
3 to the negative 1. So x should equal to negative 1. So log base 3 of 1/3 will be equal to negative 1. In general, I should have mentioned this right off the bat, but in general, any of these log functions that we're going to be dealing with, all the bases we're going to be dealing with are going to be positive integers. And then so you shouldn't have to deal with like any fraction bases or anything like that. So you shouldn't, so don't worry about that if you're trying to pull stuff out. Actually, you know what, I'm going to take that back because we're going to do some things that aren't whole numbers. Just kind of forget what I just said right there. You won't have any problems with these logarithms with the bases that we're going to be using, okay? What about this one? Log base 4 of 1.
Isn't it 0?
Right, because 4 raised to some power to get 1, the only power you can raise this to would be the 0th power. Any other power you raise 4 to, you're not going to get 1, you're going to get some other value. What about log base 3 of 1?
0.
In fact, any log base, right, we're not going to have a log base 0, we're only going to have positive log bases. Any log base that you take the log of 1, you'll always get 0. This is actually a good rule, just to remember. You can always figure it out, but that's one of our rules that we're going to use with logarithms. Okay, so log base anything because 3 to the first power is equal to 3, right? What about log base 2 of 2?
1.
1. In fact, if you ever take the log with the same base as the number here, you'll always get 1, right? That should make sense. So log b of b will always equal to 1. Okay. What about log base 5 of 0? So I'm asking, so go ahead.
I guess 0? No,
let's-
it can't be it.
Well, let's think. If it were 0, this is the same thing as saying we're raising 5 to some power to get 0, right? If you raise 5 to the 0th power, you'll get 1, right? So that doesn't work. Think about the function. What does the function y equals 5 to the x look like? Are there any x values that will give you a y value of 0?
No.
No, we said that there's an asymptote here. You'll never get down to 0. You'll never raise 5 to any power to get 0. So in fact, there's not an answer to this. So we say that this is actually undefined. So if you take any log of any base of 0, we say that's going to be undefined. So these are kind of the 3 main ones that you want to remember. The shortcuts. You don't want to get like bogged down trying to take a log 0 or something like that. That should automatically give you a little bit of a red flag when you're looking at that. What if I said log base 3 of x plus 1 is equal to 27? We want to solve this for x. Well, the easiest thing here will be to rewrite this. Oh, I'm sorry. Let me correct this. I'm going to say log base 3. What am I wanting to say? Sorry, I might have to. That's not the kind of problem I wanted to do. Sorry, I went off on a tangent. Forget what I said. Good, so you can do all of those logarithms, right? Basically just going through. You can either do them in your head, or you can go through and try to do the equation if you need to figure it out, using the properties there. The logarithms also have a couple of other properties. For example, we have 3 major properties of logarithms. The first is if you take log with a base, we'll say base b, of something times something, you can actually break this up into 2 different logarithms. This will actually break up into log base b of u plus log base b of v. Okay. Only if it's separated by multiplication. And the opposite also works. You can start here and move backwards. Okay. So a situation where this might come in handy is if you know what log base b of u is, and you know what log base b of v is, but you don't know what the combination of them necessarily is. I'm going to break up something like this. Log base 3 of, we'll say, like 9. Well, that's not a good example. Sorry, obviously I'm not thinking straight what I want to do here. This comes in handy if you know two of the logarithms. And this is where I need to go to this set of notes. That's what I forgot to do. Okay. That's what I want to do. Okay. So do you mind if I just start this little section out here? I'm just going to start with this property.
Go for it.
Alright, so we have three main properties of logarithm. So, the first one is this log base b of something times something. This will split up into two logarithms. Log base b of the first thing plus log base b of the second thing. So we can split them up. When this comes in handy is particularly going the opposite direction. So, for example, you might be asked to find log base 10 of 4 plus log base 10 of 25, right? And so it works both directions. Either you can split up going from this direction to this direction, or you can put them back together, as long as these are both the exact same base. So for example, I have no idea what power I should raise 10 to in order to get 4, right? And I also don't know what I should raise 10 to get 25. But if I take 4 times 25, that's 100. And I definitely know how to do that. So really I can think of this as log base 10 of 4 times 25. So this is log base 10 of 100. And this will be equal to just 2, right? Because 10 to the second power will equal to 100. Okay, so this is really convenient if you don't know two logs and you can end up putting them together. Something else might be one like this. Log base 8 of 32 plus log base 8 of 1/4. Again, I don't know what either of these logs are individually, but if I put these together, this is really log base 8 of 32 times 1/4. So this is log base 8 of 8. And then 8 raised to the first power is going to be equal to 1. So log base 8 of 8 is equal to 1. I could also use this to split up an expression. So something like log base 2 of 3xy. If for some reason I like to split this up, I could split this up into log base 2 of 3x plus log base 2 of y. And in fact, I could keep going if I wanted to. Log base 2 of 3 plus log base 2 of x plus log base 2 of y. Now I could actually split this up into 3 different logarithms if I wanted to. We'll find some situations where this comes in pretty handy. Okay, so that's our first property. The second property is kind of the opposite of this. So property number 2, if you take log base b of u divided by b, this will really be log base b of the first thing minus log base b of the second thing, and vice versa, right? You can go the opposite direction there as well. So kind of a similar example as before, if you have two unknown logarithms that you don't know individually, but maybe if you combine them together, you can figure them out. So I don't know what log base 6 of 72 is, or I don't know what power to raise that to raise 6 to get 72. I don't know what power I should raise 6 to get 2, but I know that this tells me I can actually put these together. This will be log base 6 of 72 over 2. So log base 6 of 36, which equals to 2, right? 6 squared is equal to 36. So 6 to the second power will give us that 36. And of course I can also split this up. So something like this, log base 7 of 1 over x. I'm going the opposite direction. I could actually split this up into log base 7 of 1 minus log base 7 of x. But what is log base 7 of 1? what power we have to raise 7 to get 1, right?
0.
Right, so that's 0. Any logarithm of 1 is always going to be 0. So I can actually just rewrite this as negative log base 7 of x. All right, and then we have one more rule that we're going to use. And that's this rule. If you take log base b of something to a power, you can actually bring that power down to the front. So it's equal to n times log base b of p. So I can actually bring that power down. This is probably the least obvious of the rules, or one that people sometimes forget about when they're solving equations. So, for example, I could rewrite this logarithm, log base 5 of 8, I could think of this as log base 5 of 2 cubed. And then I can actually bring this 3 down to the front, and I'll get 3 log base 5 of 2. Again, that doesn't help me necessarily simplify this, but it's just another way of rewriting it. Sometimes you can find a way that will help you simplify it a little bit. Something like this, log base b of x to the 10th power. Again, I could rewrite this as 10 times log base b of x. It will come right on down. Or I can go the opposite direction, 1/2 of log base 5 of x plus 1. I could actually put this one back up to the top. So this can go up here as log base 5 of x plus 1 to the 1/2 power. Which I could also think of as log base 5 of the square root of x plus 1. Okay, so that's what it means to take that up to the 1/2 power. Now we do have a logarithm that's a special base, and that's log base e. We have a special name for this. We call this the natural logarithm. Okay, and we write it as just ln. Okay, so if you ever see, for example, the natural log of x, this is the same thing as log base e of x. It just turns out that we use natural log a lot, natural logarithms, so we just have a shorthand for it, since it comes up so often. But all the same rules apply. All of these rules still apply to the natural log. Also things like this, the natural log of 1. This is still just 0, right? Because the logarithm of 1 is always 0. What will the natural log of, what should I take the natural log of to get 1?
0.
Think about it, I'm raising e to the first power to get whatever's here, right?
That's the e.
Yeah, so natural log of e. So that's why the natural log and e are cousins here, right? So the natural log of e is equal to 1. So I'll use the natural log quite a bit, but all the rules still apply. It's just a shortcut way of writing log base e. So we use this quite a bit. Let's try a couple of more examples using these log rules. So let's suppose that we know this. We know that log base b of 2 is equal to 0.33 of some base. Log base b of 3 is equal to 0.52. And log base b of 5 is equal to 0.76. And I want to figure out some other logarithms based on this. For example, given this information, I'd like to know what log base b of 10 is. Well, I could really think of this as log base b of 2 times 5, because that's what 10 is 2 times 5. And then, since I know log base b of 2, and I know log base b of 5, I could split this up into log base b of 2 plus log base b of 5, using my first property, my first rule that we went over. And so I could actually just rewrite this as 0.33 plus 0.76. I'll get 1.09. There's a couple of homework problems that use this similar method. I could also find something like this. What is log base b of 1/2? This one's kind of tricky, you know. Do you see maybe what I could do to figure this one out? Because I know log base b of 2, right? So can I write this, if I can get this as 2 to a power, then I can bring down the power to the front, right? So I could actually think of this as log base b of maybe 2 to the negative first power, because that'll be 1/2. And then I can bring down the negative 1 to the front, so this will be negative 1 times log base b of 2. And again, I know what log base b of 2 is, it's given to me already, it's 0.33. So this will really be negative 1 times 0.33. Or negative 0.33. So this is kind of another example of when I can use some of these tricks to help me figure out a logarithm. Maybe I'll do one more. Given this information, can I figure out what log base b of 0.03 is? In this case, I could actually think about this instead of 0.03, I could think of it as 3 over 100. And then I could definitely get log base b, right, if I can split this up using my subtraction rules. So this will really be log base b of 3 minus log base b of 100. I got this one's good, right? But what about log base b of 100? I could maybe think of 100 as 10 squared, right? Is that okay? And then I can bring down the 2. So minus 2 log base b of 10, because that's one of my rules. It says I can bring down an exponent.
10 could be 2 times 5.
Right, exactly. So then I could break this up instead of 10, 2 times 5. So this is log base b of 3 minus 2 times log base b of 2 plus log base b of 5. Now be careful here, it's the 2 is on the outside of that logarithm, so you have to keep it totally on the outside there. But then I can just go fill in all of these stuff. So this will be 0.33 here, and then minus 2 times, I'm sorry, this one is 0.52, right? And then minus 2 times 0.33 plus 0.76. And then we can just crunch that into a calculator and get the answer, right? Or just do it by hand, of course. But this is the idea of if you know some basic logarithms of a certain base, and you don't know the other logarithms, sometimes you can figure them out if you have the right tools. So this is how you can kind of use these rules to break things up. Any questions on this so far? So I can also use the rules to break up some general expressions. So for example, let's take an expression like this. We'll start with a simple one. How about this one? I wanna expand this into as many logarithms as possible. I wanna break this thing up and expand it out using my 3 rules. I'll just remind us what the rules are here. So here's rule 1. That if you have multiplication on the inside, you can break that up into addition. Rule 2 is that if you have log base b of u divided by v, this is log base b of u minus log base b of v. And then the other one is if you have log base b of something to a power, you can bring down that power to the front. And then you can take care of it that way, right? So here, the first thing that's wrong is the square root, right? We're not too happy with that, but we can rewrite that, right?
Half of log.
Right, so we can think of this as log base 4 of 3x to the 1/2 power. And then I can bring down that 1/2 to the front using this rule here. So really this will be 1/2 log base 4 of 3x.
We could split up the 3 and the x by using the multiplication at the top.
By using this rule, right?
Mhm.
Right, so now I can split these up. Now I do have to be careful. What is one thing I have to watch out for if I do that?
Making sure that we get the half in front of the log.
Right.
Or putting it on the outside.
Right, so it's half of this entire thing. So I have to put this all in parentheses now. So there's 1/2 log of 3 plus log of x. So I can actually keep splitting that up like that. I guess if you wanted to, you could even go a step farther and say this is 1/2 log base 4 of 3 plus 1/2 log base 4 of x, if you wanted to split up. It doesn't matter. Both of these are fine. So, the idea is that we're practicing these rules by expanding these out. What about this one? Natural log of x squared times z plus 4. Remember, natural log is just log base e. It just has a special shorthand way of writing it. Here's a question: can I bring down this 2 to the front? In order to bring down an exponent, it has to be the entire thing raised to that exponent. So in this case, the only thing raised to this 2 is the x. So I can't bring down the 2 quite yet. But I could split this up right here, right? This is x squared times z plus 4. So I can use my first logarithmic rule here that I can split these up. And so I can actually just rewrite this as, and actually I probably should have put this in parentheses from the beginning. I can rewrite this as log of x squared plus natural log of z plus 4.
Now we can bring down the half in front of the first.
Right, the 2, right?
Yes.
So now we can bring down the 2 here, and this will be 2 natural log of x plus natural log of z plus 4. Now be careful here, this one does not split up. The natural log, or a logarithm in general, is not multiplied times the function. It's natural log of this function. So I can't distribute this out and say this is the same thing as natural log of z plus natural log of 4. That's like a big algebra mistake. Don't make that mistake. This is as simplified as I can get. So never think of it as logarithm times an expression. It's always logarithm of an expression. And you can't multiply that out. So that's as far as I can go on the right-hand side there. I can't do anything more with that natural log. What about this one? Log base 3 of the cubed root of 3x over x plus 4. Let's split this up as much as possible.
The cubed root is just the 1/3 power.
Okay, so I can rewrite this as 3x over x plus 4 to the 1/3 power.
Bring that to the front so you get the 1/3 log.
Okay, so bring the 1/3 down. That.
And then we have the division, which you can change it into subtraction.
Okay, but I have to leave that 1/3 on the total outside, right?
Yep.
So this will, I can use the second rule here, log base 3 of 3x minus log base 3 of x plus 4. And the only thing you could do from here, you could split this up into 3 and x if you wanted to go an extra step. For this class, it's fine if you get to the constant times an x for doing an exercise like this. So that will split up just like that, just fine. And then you can leave the 1/3 on the outside, that's fine as well. Is that all right? Any questions about those? So these are they're not too bad once you get the hang of them. But you can also go the opposite direction too, right? So I can give you, something like this. So like 3 times the natural log of x plus the natural log of z minus 7 natural log of y. And now what I want to do is combine these logarithms. Now here's the trick. You can only combine two logarithms at their exact same base. So if you have something like a log base 3 and a log base 5, so something like this, these will not combine into log base anything of x times y, because these bases are not exactly the same. So like in a case like this, I can't actually combine these logarithms. This is as simplified as I can get. But with this one I can, right, because they're all natural log. They're all log base e.
Would you start by putting the powers up first though?
Right, exactly, yeah. You want to go through and put all the powers up first before you do any combinations. So this, instead of 3 times natural log of x, it will be natural log of x cubed. And this one doesn't matter here. This is just natural log of z. And then this will be minus natural log of y to the 7th.
Then I think you'd want to put the division back together, so the subtraction part of it.
Okay. Yeah, you can do these in any order, as long as, don't try to do all 3 at the same time, because it's easy to make a mistake if you do that. So do 2 at a time at every step when you're putting them back together. So you said maybe do the division one first?
Mm-hmm.
Okay, so I know that using my second rule over here, I can put these together by saying natural log of z divided by y to the 7th. And then what could I do next?
Now it's the x to the cubed times that.
Right, so using my first rule up here, going the opposite direction, this would be x cubed times z over y to the 7th. Or I could just combine this and make this x cubed z over y to the 7th. Let's do maybe one more. formulas. So how about this one? 2 times log base 5 of x plus 1/2 log base 5 of y. Okay, so what do you think?
Start by putting the powers back up.
Right, always start by putting the powers to the top before you start combining things. So I'll put the 2 back up here. So this should be log base 5 of x squared using my rule number 3. This will be log base 5 of y to the 1/2.
Or the square root of y.
Right, so we can again rewrite that as the square root. Log base 5 of the square root of y.
And then you can multiply them together.
Right, then we can use our first rule here, since they're exact same base, 5 and 5, this will be x squared times the square root of y. And this is as far together as I can put it. So you should be able to go either direction. I should be able to either give you this, and you can split it up this far, or I should be able to give you this, and you can go back the opposite direction and put them together. How about one more quick one? Natural log of e 3 times e squared. I could actually split this up into addition, right? So natural log of 3 plus natural log of e squared.
Move e squared in front of the ln e.
Right, and that's what I would do next. I could pull that 2 down, and I'll have 2 times natural log of e. But why is that good in this case? What is the natural log of e going to be? It's the same thing as saying log base e of e. So e raised to the first power should be e, right? So the natural log of e is actually just going to equal to 1. This is one we'll see a lot. Whenever we can take natural log of e, that's good because it turns into 1 and goes away. So this will actually just turn into natural log of 3 plus 2 is another way of writing that. We should get the exact same answer. Okay, so one more thing with the logarithms before we actually go and see how we can use them in some equations. And that's what's called the change of base formula. So I can change the log bases to any base that I want to using a formula. And the formula is just this. If you have something like this, log base b of x, if you want to change this into another base, say we want to change it into base a, we can always do that by taking log base a of the big number and then divided by log base a of the base. Okay. The reason that you might want to do this is because most calculators will only do logarithm base 10. So if you want to actually figure something like this, for example, on your calculator, what is log base 2 of 3? Well, most calculators don't have that option to plug that in. Most scientific calculators at least. So I could actually rewrite this. This would be the equivalent of log base 10 of 3 divided by log base 10 of 2. So in your calculator, when you plug that in, you'll get log base 10. And you can just take log of 3 divided by log of 2 and figure out what this answer would be. One thing I should note that on a calculator, and also sometimes the shorthand, if you ever just see LOG, that's the same thing as log base 10. Okay. So these are our two abbreviations. Or LOG is sometimes just log base 10, and LMN is the same thing as log with a base of e. These are the two most common ones. This one's common, of course, because we have base 10 number system, right, and 10 fingers and all that sort of stuff. So the log base 10 comes up quite a bit. But you could also take, for example, log base 5 of 3. If you wanted to write this in terms of natural logs, for example, you could always rewrite this as natural log of 3 over just natural log of 5. So it's pretty easy. You just kind of force it to be a certain base, and you take this number, and then you can divide them through like that. Okay, so the last thing I want to do is solve some equations with logarithms, right? So I know it's kind of a lot of new stuff. Is any of it?
Some of it's familiar.
Okay, but is it all? None of it's like super over your head or anything like that. Okay. Sometimes I can't